There's one uncomfortable truth. We don't have a step-by-step construction manual for the Great Pyramid. No blueprints, no daily logs, just stone, geometry, and a few quiet clues left on a desert plateau. So this isn't a video that claims the one true method. It's a video that separates evidence from guesswork. We'll mark what we know, what's likely, and what's still debated, then test the leading ideas like an engineer. Because the real mystery isn't magic, it's how a human system scaled up without modern machines. 3 questions drive everything: how they moved blocks, how they kept the pyramid aligned, and how they built it safely. If you've ever heard aliens or lost technology, pause for a second. The stones don't demand that story. The stones demand planning, quarrying, transport, labor, and quality control over and over for years. And here's the twist. Every popular theory solves one problem, but creates another somewhere else. By the end, you won't have certainty, but you'll have a short list of solutions that actually fit the constraints. Think of this as a reconstruction with honesty. We only trust what the site can support. Let's start with the simplest layer. What we can verify just by looking at the pyramid and its landscape. The Great Pyramid sits on a broad limestone plateau. Its core is mostly local limestone, not one exotic material. Some stones are huge, but many are manageable by coordinated teams. Still brutal work, but not supernatural. Inside, there are chambers and passages that had to be planned early, not improvised at the end. The upper chambers use heavy granite harder to move in place, so the logistics weren't uniform across the project. We also know quarries existed nearby, and the Nile floodplain shaped transport seasons and routes. Even without perfect records, you can read a project in its leftovers. Roads, ramps, debris, tool marks, staging areas. But the biggest missing piece remains the same, the exact lift system for getting stone up the growing height. That's why we'll use a rule. Prefer explanations that reuse simple tools many times instead of one impossible trick. Next layer, the people. This wasn't one genius. It was a workforce with supervisors, schedules, and supply lines. You can't feed thousands without accounting: grain, water, shelters, medical care, and rest rotations. If the food chain breaks, the build stops. So logistics is not a side story, it's the core technology. Think in shifts: quarry teams, hauling teams, placement teams, and finish teams, all moving like a factory. The pyramid's precision suggests standards, repeated measurements, corrections, and inspectors who rejected bad fits. And that leads to the next question: how did they keep the base level and the line straight across so much distance? Because if your foundation is off by a little early, the error grows with every layer you add. This is where the mystery gets practical. Geometry, leveling, and orientation skills ancient builders absolutely had. The pyramid is near perfectly square and remarkably aligned to the cardinal directions for its time. The site tells us they cared about alignment enough to build systems that could maintain it day after day. First, leveling. Before stacking blocks, you need a reference plane, a flat truth to build on. You can do that with simple tools: sightlines, water channels, plumb bobs, and repeated checks across the site. Not glamorous, but it's how you stop the project from drifting as thousands of blocks go down. Second, right angles. Long straight edges are rare, so builders rely on geometry triangles, chords, and consistent units. The goal is repeatability. The same process gives the same corner, even if different crews work different days. Third, north. Without compasses, you can still find directions using the sky stars, shadows, and careful observation. We can't prove one exact method, but we can say this: the alignment took planning, time, and trained specialists. And that planning ties directly into the bigger problem: moving stone across distance, then lifting it higher and higher. So let's talk. Transport, the part everyone imagines as pure muscle, when it's really physics plus organization. Quarrying isn't just cutting stone. It's controlling break lines, sizing blocks, and reducing waste you can't carry. The easier you shape at the quarry, the less chaos you face later at the placement line. For local limestone, the route might be short. For granite, it's a different story: longer distance and heavier handling. Over water, friction drops. Over sand, friction becomes the enemy unless you manage the surface. One practical idea: sledges. Place the block on a wooden sledge, then pull as a team on ropes. Modern tests suggest wetting sand can reduce drag. That's not magic, it's controlling friction with water. But sledges only solve horizontal motion. You still need staging. Where blocks queue, where they're sorted, where they're checked. Imagine a supply lane. Blocks arriving, measured, corrected, then handed off to the crew working at that height. If a block arrives late, the entire layer slows down. So the build needs rhythm, like a conveyor belt made of people. Now comes the famous question: ramps. Everyone has a ramp theory, because ramps are simple and plausible. But ramps also have a problem. The higher you go, the more ramp you need, and the ramp itself becomes a mega project. That's why we treat ramps as a family of options, not a single answer. Let's test the main ones. Option 1, the straight external ramp. Easy to imagine, easy to start, and uses basic materials. Its strength is simplicity. You can build it fast, widen it as needed, and move lots of blocks in parallel. But as height grows, the straight ramp has to be insanely long or insanely steep, or both. A long ramp means huge extra volume of mud brick and rubble, plus constant maintenance after wind and traffic. And here's the catch. If the ramp is massive, where did it go afterward? And why don't we see more clear traces? Option 2, a zigzag ramp on one face. Shorter total length, less material, and it climbs as you build. It also keeps the ramp near the work, which is efficient. But it creates corner turns and traffic bottlenecks. Tight turns are hard with big blocks, and a ramp hugging one face can obstruct precise casing work. Option 3, a spiral ramp wrapping around the pyramid. It stays relatively close and doesn't need one giant runway. A spiral solves the too long problem, but it hides the corners, the very places you must keep sharp and aligned. If the corners are covered, how do you verify straightness and angle during the critical mid-build stages? Also, a spiral changes the loading on edges and faces. You'd need careful control to avoid damaging finished sections. Option 4, an internal ramp. The idea is a hidden passage system inside the pyramid body itself. The benefit is elegant: less external debris, protected pathways, and no need to remove a monster ramp at the end. The downside is equally serious. Internal ramps are hard to ventilate, hard to turn in, and hard to prove archaeologically. You can't just claim an internal ramp because it sounds neat. You need evidence of corridors, voids, or consistent patterns. So which option wins? None wins completely. Each one buys you something, then charges you somewhere else. That's why many researchers suspect a hybrid, an early straight ramp, then switching methods as the pyramid rises. That hybrid idea fits a real construction mindset. You change tools when the constraints change. Early stages need speed and bulk movement. Upper stages need precision and safer handling on narrow working platforms. A reasonable sequence is fast external access early, then smaller ramps or lifting tricks closer to the top. And lifting tricks doesn't mean cranes. It means levers, simple machines used repeatedly with discipline. With levers, You can raise a block step by step. Lift, pack, reset, lift again. Slow, but reliable. If you have enough teams, slow methods still scale. The pyramid is big because the system runs every day. Now, let's address the precision myth that blocks are laser cut. They aren't. They're good stonework and clever fitting. The core stones can be rougher. The outer casing demands more accuracy because the surface makes the geometry visible. That explains a pattern. Move fast on the inside, then invest labor on the outside where mistakes show. Another overlooked constraint is safety. A high platform with heavy stone is a constant injury risk. So you design workflows that reduce chaos, fixed lanes, clear signals, and specialized crews for placement at height. And this is where ramps again matter. They're not only about lifting, they're about controlling people and traffic. Too many workers in one narrow place is dangerous. Too few workers slows the schedule. The system has to balance. Now let's step inside the pyramid, because the interior is a clue to sequencing and engineering logic. The major chambers aren't random. They sit within a load path, and the builders had to manage pressure from above. Heavy stone overhead wants to crush voids. So you need relieving strategies, angled blocks, stepped roofs, or staged chambers. These features tell us the builders understood forces, even without modern math. They learned through tradition and testing. Granite beams in the upper chambers are a major operation. They imply careful planning for transport and placement. You don't casually move granite at that scale. It means the project had high-priority materials with dedicated logistics. And that again suggests the pyramid was not one continuous improvisation. It was planned in phases, with milestones. If we zoom out, the build likely felt like a cycle. Quarry, haul, lift, place, check, then repeat, thousands of times. Small errors would be corrected constantly. That's how large projects stay straight. Not perfect workers, but constant correction. So why are we still missing certainty? Because the most temporary parts, ramps, wooden tools, ropes don't survive well, stone survives. Mud brick washes away, timber rots, ropes vanish. The very machine of construction is mostly gone. That forces us to reason backward from what remains. Geometry, scars on stone, and the footprint of the worksite. It's like solving a crime where the weapon disappeared, and you only have the marks it left on the wall. Now let's talk time. Estimates vary, but the project likely took decades, not centuries, and required consistent state support. Consistency matters more than speed. You can do incredible things if you can keep a workforce supplied for years. That's why the "who paid for this" question is real. Administrative power is part of the technology. Skilled stonemasons are one layer. But so are planners, scribes, foremen, boat operators, cooks, and medics. The pyramid is often described as a tomb, but as a project, it's also a demonstration of centralized coordination. Now, a quick myth check. Precision doesn't require advanced machines. It requires standards, tools, and patient repetition. Moving heavy stone doesn't require anti-gravity. It requires friction control, leverage, and enough trained hands. And impressive alignment doesn't require satellites. It requires careful observation and the willingness to redo measurements. The real secret might simply be this. The builders were professionals, and their work culture was optimized for the task. So what's our best fit story so far? A phased build, early bulk movement, later precision with ramps that evolved. Transport likely mixed land and water routes depending on season and material, with sledges and managed surfaces. Lifting likely used ramps where practical, then smaller ramping and levers as space tightened higher up. The casing and finishing demanded specialist crews, because the outer surface defines the pyramid's final geometry, and the interior shows an understanding of loads. You don't survive thousands of years by guessing every critical beam. But let's be honest, this is still a model, not a proven instruction manual. The gaps are real. That's why the ramp debate still matters. If we find clearer traces, the leading model could shift tomorrow. So, the best attitude is humility. Strong claims require strong evidence, and evidence in archaeology is uneven. Still, the range of plausible solutions is smaller than people think. Many popular ideas fail basic constraints. The pyramid wasn't built by one miracle. It was built by repeating simple methods at scale with strict control. And that is a lesson modern builders still recognize. Organization beats fantasy when you're moving real materials. Before we wrap, here's one final angle. Why build this way at all? Because monuments are political as much as spiritual. A project this large communicates permanence, authority, and order, especially in a world where most things decay fast. The pyramid's shape is stable. Its message is stable, and that stability is engineered, not accidental. When you stand at its base, the scale is overwhelming, but the logic is grounded. Layers, lines, and controlled labor. That's the paradox. The more human the method becomes, the more impressive the outcome feels. So, if someone asks, how did they build it? Your best answer is, we don't know one method, but we know the constraints. And within those constraints, a hybrid of ramps, sledges, and levers, supported by strong logistics, fits the evidence best. The remaining mystery is the exact choreography. Who did what, when they switched methods, and how they standardized it. Next time you see the pyramid, try this. Imagine the supply line, not the finished shape boats, sledges, levers, and teams. Imagine the daily repetition. Measure, place, correct, then do it again, thousands of times, under desert sun and wind. That's the real wonder, not one trick, but a system that kept working long enough to turn stone into a message. Thanks for watching WorldBuilds. If you want more engineering mysteries like this, hit subscribe and stay with the series. Drop a comment with your favorite hypothesis and what evidence would convince you to change your mind. See you in the next build, where we'll test another monument with the same rule. Evidence first, story second.